All right, so today we are going to finish exponential distribution, gamma distribution, and start talking about normal distribution. And we are going to see how we can solve certain gamma distribution related problems by using the Poisson distribution. There's the Gamma-Poisson formula. So that's what I need to go over today. And I'm going to also solve examples as we go over them. And on Thursday, the quiz is going to be about this chapter 4, one of the distributions that we are seeing in chapter 4. Okay, as a reminder, last time we have entirely covered the uniform distribution, which has a constant probability density function in a finite interval from A to B. And this A to B can be standardized to 0 and 1. The standard uniform distribution is between 0 and 1. And any non-standard uniform is just a scaled and translated version. So which means that it's a linear function of the uniform distribution. So they can be converted from one to other easily. And exponential distribution, we started talking about it. It's about waiting times. And here it has the same parameter. The lambda parameter is the same as the one in the Poisson distribution, where it shows the average number of events that occur in a fixed time interval. For example, number of accidents in a day. In Ankara, I gave this example. That day is a fix in a single day, or number of subscriptions to for example, number of new users in YouTube in a day is 2000. So this one, lambda is 2000, our time interval is a day, and that was Poisson distribution. And here, exponential distribution is related to Poisson in a way that what's the waiting time between two of the events? What is the waiting time until next user joins YouTube? Or what is the waiting time until next accident? What is the waiting time until the bus arrives? For example, if in some place, if a bus arrives 5 times in a bus station in an hour, so the waiting time until next bus can be modeled as an exponential distribution if the average number of those rare events are Poisson with parameter lambda. Okay, we have seen the shape of Poisson changes with respect to the lambda parameter. As lambda gets larger, it looks similar to the normal distribution with like a bell-shaped curve, but don't forget that the domain of Poisson distribution starts at 0. We can observe 0 events in that time interval, or we can observe infinite events. It goes to 0 to infinity, so its tails are not symmetric as normal distribution, as we are going to see, and therefore, although it looks like normal, it's not normal distribution. But we are going to see that gamma distribution also looks like Poisson when with certain cases. So we can actually we'll be able to use the Poisson gamma formula to solve certain formulas we are going to see. So this figure also shows the relationships between the Poisson and exponential random variables. So when number of events in 1 minute is given to you as a Poisson random distribution, so this should be given, all right? So you may actually answer, how do we know that they follow the Poisson formula, the number of rare events in a time interval? In real life, they may not always follow Poisson distribution. There may be other factors that affect the number of events happening in a certain interval. But usually when you have rare events, meaning that again the rare event, this definition does not mean that it has to happen once in a year or once in every 10 years. The definition of rareness is like we don't expect 2 events to happen simultaneously at the same time. So there is some time interval between 2 events. If such events can be considered as rare events. For example, you cannot consider the raindrops falling on a plate, a rare event, because simultaneously multiple raindrops may be falling. Okay, so you may have to model it with something as different. But most of the time, when we observe these real life events, the experiments from practice, we see that many of such rare events actually follow Poisson distribution. So if you collect certain statistics in an area, so we are going to talk about this, especially in chapter 9. Chapter 9 and 10 is about statistical inference. Right now, we are always in probability. All these things are given to us. All right, we are saying we have a random variable that follows this. We have a random variable that does this, and we are asked probabilities directly from those given distributions. The area of statistics, on the other hand, is trying to infer these distributions from data. So we are going to collect some data, and we are going to see whether that data follows Poisson distribution or not. So we are going to perform tests. So this is really good. We are going to see if you make certain observations and you look at data, for example, what is we are going to infer the lambda from that. For example, inference of the lambda is going to be easy if you just observe it for a year, for example, and you look at daily averages and average that over a year. That may be a very good fit for lambda, and you may also check whether it's a good fit for Poisson distribution, whether your data, your observation, which are daily observations, whether they fit Poisson or not. So we'll be able to perform such tests. But we see that in many real life events, rare events that do not occur simultaneously like this, actually follow very closely. Poisson distribution is a very good model to model those, and that's why we use that. All right, but there are other distributions. So this is like an introductory probability and statistics course. These are not the only distributions. There may be other non-parametric distributions, other family of distributions that we don't cover in this class. So just bear in mind that for different cases, different distributions are maybe applicable, but these are really common, most popular distributions that are used to model certain types of probabilistic events. And one such probabilistic event is the waiting time. How long until the computer crashes, for example? How long until the next bus arrives? Or how long until the next packet arrives in the network? So they are used in communication networks, in predicting hardware failures. So these are all applicable family of distributions. Now, let's get back to this exponential. If again we are given that there's a random variable which tells us the number of events in 1 minute is a Poisson random variable with lambda is equal to something. Another variable n2, if we're asked that what is the number of events in 2 minutes, or what is the probability that we will have at least x many events in 2 minutes, when we increase the time interval, it becomes another Poisson variable, this time with 2 times lambda. So, okay, so this is important about exponential distribution and also Poisson distribution. So these are about Poisson. And in general, if we're asked probabilities about what happens in t minutes, the number of events that happens in t minutes is less than this or more than that, then it becomes a Poisson random variable with t times lambda. Okay, we have to scale whatever your unit is. If you're given an accidents in a day, if you're asked the probability what happens in accidents in a week, you have to 7 times lambda. It will be your random variable that models that Poisson. And the relationship of exponential is that the time interval, if you look at time intervals between events, or when you're at some arbitrary place, okay, you may be here, not between the 2 events. You may be, let me also increase my mouse pointer size. So wherever you are in time, you may be here, right under the mouse pointer. The time until next event is an exponential random variable. Okay, so there is exponential. We are going to see that exponential variables have a property which means that conditionally the fact that an event did not occur in certain number of minutes does not actually affect when the next event is going to happen. It's always from your current position. Time until next event is always an exponential variable, independent of whether you know that the event did not happen in the last 10 minutes or 15 minutes. So from your current position until the next event, it's the same exponential random variable with the same parameter lambda. So that's really counterintuitive. And that's why I mentioned this last time, I guess, the gambler's dilemma, which is if you are playing in front of some, you're a gambler and you're playing in front of a slot machine, and you know that you didn't win the prize in the last 2 hours. You always, since I didn't win it in the last 2 hours, you expect to win soon, but it doesn't actually matter. The how long you have waited does not change the probability that you are going to win in this many tries. So the probability that you're going to win in 5 tries, for example, doesn't, I mean, it's the same whether you start from new or you know that you haven't won in the last 1 million tries. Okay, so so this is what the memoryless property of exponential. And the example that I gave was the number of tries. It was geometric distribution. So geometric, it was a continuous case of exponential. If we have number of tries, which is some integer, it becomes a number of tries until the first success is our geometric random variable. And the time to wait, if we perform every try in some unit of time, actually we can have exponential, we can also model it as time. But if it's continuous, it means that it can happen anytime, even between tries, then it becomes a continuous random variable, and that's what exponential is. It's a continuous case of geometric, and it has this memoryless property that I'm going to show you how we can derive mathematically. So this can be mathematically proven, that conditional probability, that knowing that some event is going to happen after some time t. So it means this. Let me draw it on GIMP. So if we have, so here, if this is our time, so actually I think we have a better figure in the book. Let's see, do we have it? No, we don't have that figure. We just have this description. But what it means is that, imagine we have the exponential distribution PDF that is like this. All right, I'm going to draw the PDF fx, and this is that time, actually, not fx, let's call it ft, because we're modeling time, let's call it t. Okay, now what this memoryless property is saying, that given that the time to wait is, for example, so this is 0, this is t. Okay, this is the waiting time. So given that you had waited t minutes and you didn't observe this, what is the probability that it's going to happen in the next x minutes? Okay, so the probability that it is going to be less than, the probability that t is going to be less than or equal to t plus x, given that given that it didn't occur in t, okay, in the first t. So given that t is greater than t. So this one is that knowledge. Given that I know that t did not happen, I mean, I did not observe this event in the first t minutes. I know that t is greater than t. What is the probability that I will observe it in the next x minutes? Okay, so this is like the gambler has observed this and have seen that it didn't happen in the first t minutes. What is the probability that it will happen in the next x minutes? is equal to that probability, the unconditional probability that t is less than or equal to x. I think it's I did wrong. Yeah, or I mean the this one, it's reversed here. Okay, so here the t is maybe I wrote this t. We know that this t is less than x is this waiting time here. Okay, so the waiting time until the next event after, maybe I should write this as t plus t less than x. I mean, if this t is, I write it beginning on this axis, all right? So given that it's not here, the probability that it's in this location is equal to the, since you know that you're currently at this time, the probability that you will wait t minutes after this time, and the probability that t is going to be less than x is the same thing. Actually, what I wrote here, I think, was correct. The probability that this t is less than or equal to x, they're equal. So in other words, this ratio, if you take a look at this x over 1, this is the entire area under the curve is 1, is equal to whatever you have here. If you know that in the conditional probability, you know that the event did not occur here, so your distribution becomes, your sample space becomes this part. All right, so the probability that if you look at the same x here and you take the ratio of that x over this remaining area here, which is the summation from t to infinity, that PDF fx dx, these are equal to each other. So it's like the shape of the exponential distribution is like it's the same. This ratio is being the same overall until infinity. So it's like a fractal. The shape of the exponential, as you zoom in, zoom in, zoom in, it's the ratio of this region. Actually, when you're zooming in, you're also, since your axis interval is same, it's not like the same as zooming in here. You're actually also increasing the axis constant here. The interval that you're talking about is constant. So as you're zooming in, that interval you're looking for is going to get larger. It's not like the shape is always same. As you zoom in, that x gets larger, and this ratio to the remaining area to the right hand side is they are equal to each other. So that's called the memoryless property, and it's written in a different way here, not the probability. I was asking like the conditional probability that is going to be less than x. So if you take 1 minus these things, the complement, it's the exact same thing actually. So this one, again, we are given that this t is greater than, so here t is our random variable. Okay, it's not that constant point in time. In my case, that small t was the random variable. Sorry for the term mix up that compared to the one in the book. So t is our random variable. The probability that the time I will have to wait more than x minutes is equal to, given that the probability you have waited t minutes already. Okay, so the waited for t minutes, so this is the waited time. We have already waited for t minutes and we haven't observed it. We know that. The probability that we will wait additional x minutes is equal to the initial unconditional probability of waiting x minutes anyway. So this means that, let's go back to the slides. This means that in this figure, whether you're here, the waiting until the next event is still the same probability. Whether you are here or here, the hand is here, whether you're at this event, the probability that you will wait on the probability of the time until next event is still an exponential with parameter lambda. We don't change this lambda depending on how much time we have waited. And this was the Poisson PMF function, if you remember, and the PDF and the cumulative distribution function of the exponential could be derived from this. which is from this statement, which we covered last time, if you remember again. The waiting time for the next event is greater than t time units. So, this is like saying that this is the complement of the CDF. We are in the CDF. We are looking for what is the probability that we are going to wait less than t time units, right? But this one, if we compute this, which is the probability of having 0 events in that time, is the inverse of the complement of that event. So which means that 1 minus e to the minus lambda will be our, the CDF function. So you have to wait at least t time units, means that 0 events occur in t time units. So we change our lambda to this t time units if lambda is given to us as a single time unit. Okay, so for example, lambda is given to us as in hours. So whatever this t time is, we have to convert to that, and this t is the actually the exponential random variable. So we are going to write lambda t here. We don't know what this t is. That's our random variable. If x is our Poisson random variable in t time and t time units, it will be a random variable that t times lambda. Okay. And this is the probability to observe 0 events in a lambda t Poisson variable, which is e to the minus lambda t if you just plug in 0 here. So this is the probability of observing 0 events in t time units, meaning that the probability to observe your event in less than t time units is 1 minus t, which is our CDF function. So this is the exponential cumulative distribution function, which gives the probability to observe the next event in less than t time units. And by taking the derivative of this, we get the exponential probability density function, which is lambda e to the minus lambda t. Again, you do not need to memorize these formulas at all. We are going to give these formulas to you in the cheat sheet in the midterm exam, but just know that the relationship between them. So Poisson is how it's related to exponential. And in summary, if you compute the expectation and variance, these are what you get. In order to compute the expectation, we need to multiply this with x and take the integral from x 0 to infinity. And if we solve that mathematically, we get this 1 over lambda. In order to compute variance, we need to multiply this term with x squared and then take the integral to find the expected value of x squared, and subtract from it 1 minus lambda squared, which is the square of this expectation. Okay, that will be our variance, and this is what we get. We talked about this memoryless property. So this is explained on an example. What is the chance that an electric component A survives x hours? Which is here exponential random variable is the x, which is time to failure. If we are given the parameter lambda, the probability that x is greater than this x is basically 1 minus CDF. So it's the complement event of CDF, right? In CDF, we ask what is the probability that it's going to be less than or equal to this. Now, if you're asked something, what is the probability that it is larger than this? It's the complement of the CDF, basically, which gives us 1 minus the CDF, this. Now, if you know that another component B, which has exactly the same exponential distribution with the same lambda, if you know that it did not fail for t hours, it's been working for t hours, what is the probability that it will also survive another x hours? So this means like a smaller probability than what A has, right? So when we are asked, we know that this probability x is greater than t. It didn't fail in the first t hours. What is the probability that it's going to survive another x hours? If we solve that, and here we can use the Bayes theorem to do that. Okay, so this is exactly the Bayes rule. So the probability of x is greater than t plus x and x is greater than t. So they are actually two events that are subsets of each other. Okay, so therefore this right hand side cancels out because it's already, this event is contained entirely in this one. If x is greater than t, yeah, exactly. If you're right. I mean, if components, if you also take into account that the components actually over time they get older and they're more likely to fail, then it will not actually make sense to model that as with exponential. All right, so you may be right. So this one assumes that it fails, and then until the next failure, we have another. All these things are independent. These things that we observe, but they get more volatile to damage over time. You're right, and it wouldn't be memoryless. You will have to take into account the time in that case. For example, of course, when you, I mean, this is really counterintuitive in case of such, if you think about the mechanical things. I mean, modeling them as with exponential will not make sense. If you know that you bought something brand new, it will not have the same failure to time to failure exponential random variable as another device that has been working for 2 years with no failure. They are two different things. So they will have you will have to maybe change your exponential random variable over time. That lambda has to change as the electronic components they are now more volatile to damage. You're absolutely right. So this is assuming that we have the same exponential distribution with the same lambda, which doesn't change over time. And in that case, when we solve this, you see we get the same e to the minus lambda x. So this is exactly the same as x greater than x. So knowing that x is greater than t doesn't help. So this is called the exponential distribution. So for devices which can get damage over time, so having an exponential random variable for them may not be the right thing to do. But if you think about like bus waiting times for buses or waiting time until the next win, they are exponential. There is nothing, time does not work on them, time does not damage them. So therefore you may, if time does not affect the distribution or the occurrence of the event itself, the amount of time that has passed, then it's still exponential with the same lambda, then you can think about the memoryless property. Otherwise, it will be different, right? I mean, it's also like human aging, for example. A person, if when you say, for example, a person gets sick every month, this changes as age changes, right? So, but usually when you're therefore modeling such thing, how long do you get sick? How often? What is the average sickness of a person? You usually model these between age intervals. You say that people between the age of 45 and 55, they get sick twice a month. So for those period of time, that may be an exponential random variable, and that's only applicable for people between that age. All right. So again, we will assume that's a very good point. When we think about exponential, all these events, time does not have effects on them. Okay, in terms of damaging effects, and therefore it doesn't change whether how long you have waited. The memoryless property comes from the fact that you have the same exponential over a certain interval. So this concludes our discussion on memoryless, the exponential distribution function. I'm now going to continue with the gamma distribution, which is actually a generalization of the exponential distribution, where just like negative binomial is a generalization of geometric, the same relationship with gamma and exponential. Instead of waiting or waiting for the next event, we will be waiting for k events. In this case, the name is not k. In the continuous case, we have alpha. So we'll have two parameters, alpha and lambda. Lambda is still the same. Alpha will be considered as, if you consider it as an integer variable, it's like alpha number of events. What is the waiting time until alpha number of events? X is the random variable that shows the waiting time after alpha number of events occur with the same lambda. Lambda events occurring on the average in a time interval. That's the gamma distribution. And interesting thing about gamma is that alpha does not necessarily be an integer. It may be that alpha, we may have that also as a real valued parameter, and it may then used to model very different things, not only waiting times, but for example, money spent, electricity spent, or uh, water flows, the amount of water flowing in a certain region. So gamma distribution can be used to model these resources, spending of these resources. Okay, and we are going to see that it's a generalization of exponential, but it's not, as I said, it's interestingly not only used for to model time, but these different resources that are spent, like weight or amount of flow or amount of energy that is spent. So let's talk about the gamma distribution next. And I will solve an exercise example about gamma distribution, which shows uses the Gamma-Poisson formula, converting a gamma variable to a Poisson variable, and then solving the problem by using the Poisson table. We will get exactly the same random variable probability at the end. So it's the random variable is defined as a total time of observing alpha rare and independent events, each with exponential waiting times. So imagine we're waiting for buses, and each bus is following the same parameter. We have 5 buses on the average arriving at a bus station in an hour. So lambda is equal to 5. Then if we think about things like if somebody says that I'm going to get on the 10th bus that is coming here. So I don't want to get on the first 9 buses. I want to get on the 10th bus that comes here. Alpha becomes 10 in that case. Your waiting time to get on the to get on the bus, since you have to wait for 9 buses and get on the 10th one. So alpha becomes 10 with lambda again equal to 5 here. 5 buses on the average in an hour doesn't change. So alpha and this lambda are independent parameters. And if you take a look at this, since the waiting times between every bus arrivals at the station, they're all exponential, it becomes the x is actually a sum of alpha exponential random variables. And therefore its expectation is alpha over lambda because of linearity of expectation. Again, we can use linearity of expectation to compute variance as well. The formulas are very, very similar to the ones in the numerator are replaced by alpha, and that's your gamma variable. Its PDF, on the other hand, is actually a little bit different because these events, they can, just like the combinatoric case we had in the negative binomial, the first k-1 events combinatorically being able to disperse in different places in the trials. Here we can have the same thing with alpha. Therefore, in terms of combinatorics, this PDF becomes something complicated. And here is its PDF. So we have similar to the first alpha minus 1 events, x to the power that e to the minus lambda, and lambda to the power alpha divided by this gamma function. This gamma function is nothing but, for integers, it's just defined as alpha minus 1 factorial. It's just a factorial function which just reduces this alpha by 1. But the reason that it has this strange name, why do we call it gamma function? What is so special about it? It's actually a function that is also defined for complex numbers. we are not going to see that's it's used for complex numbers. But gamma function in general, if you look at Wikipedia, for example, you can learn more about the gamma function and see how it has a real, how it works. It has a real component and an imaginary component, and it works on, it's a function that is defined on complex numbers. But for us, it's going to be, when alpha is an integer, we'll be just using this factorial. When alpha is not an integer, let's see whether it works or not. For example, let's get back to Octave Online. Probably we have the statistics package that have this gamma function. So gamma 5. So I need to write, okay, 24. As you can see, so gamma is 4 factorial, right? 4 times 3 times 2, it's this. So gamma works like just like factorial. Gamma 6 is 120. But one thing that is interesting here is gamma 2.5. You can also compute that. All right. This is not, I mean, if you just define gamma as a factorial 2.5 will be something undefined, but the gamma function is defined for also non-real numbers. It probably has a rather complicated formula, and therefore the book doesn't even mention that, your textbook. But if you're going to use Octave Online to solve some problems where alpha is not an integer, you will be referring to that PDF, or you may use this formula with an arbitrary non-integer gamma function. So gamma 2 is 1, right? Factorial 1. And gamma 3 is 2. So anything between 2 and 3 is between 1 and 2. It's like an increasing function, just like factorial. So this is its PDF here, and alpha doesn't need to be an integer. For values of alpha greater than 1, gamma function looks like a bell-shaped curve, but again, it's not symmetric. It starts at 0 since gamma is just like exponential. Gamma is for like waiting times. The smallest value it will get, its domain starts at 0. Our random variables, if it's their exponential or gamma, they cannot be less than 0. So they start at 0. When we have alpha is equal to 1, we have the same thing as exponential. And interestingly, alpha can be less than 1 too, less than 1 as well. So it will have it will behave like an exponential, which just decreases really quickly. And for values greater than 1, it behaves like this. And the gamma function, actually, yeah, I have that. It's not in the textbook, but I have the gamma function from some other course. The gamma distribution is written as an integral from 0 to infinity of this x to the alpha minus 1 e to the minus x. So this is like our combinatorial case where the first alpha minus 1 events can occur anywhere within this interval, and this is our occurrence of that event at x. We were using e to the minus lambda x, if you remember, in the exponential distribution. So this is like that combinatorial function that we had for negative binomial extended over to continuous case. So this is how it's defined. It's just an integral, and its behavior is like this until 1. It starts at a very large number. Okay, so until 1, it's not. It's actually, and until 2 here, it's like a maybe decreasing function. Then after 2, it starts increasing, like as the factorial increases. This increases in parallel with the factorial function. Okay, so this is like factorial 1. At this point, when alpha is equal to 2, we have factorial 2 minus 1, factorial 1. So we're exactly at 1 here, and after that, the increase is similar to that. So this is what the gamma function looks like. And the gamma distribution, as I also told you, it's also widely used to model random variables other than waiting times. since when alpha doesn't need to be an integer, amount of money spent, amount of resources used, electricity, gas. So there in the book there you'll see exercises which says that the number of money spent is a gamma variable with this alpha and with this lambda. In that case, when you think about amount of money spent, you forget about rare events. There are no waiting times. You just treat the think that alpha divided by lambda as the expected value of the money spent. Okay, so the whatever lambda is and whatever alpha is, you just look at the expected value as the average money spent for this random variable. Okay, and here so the last thing I'm going to talk about today is this Gamma-Poisson formula, which allows us to solve gamma random variable related problems by using the Poisson distribution. So they are related. So it's maybe you have to take your time actually to understand again this, how two random variables are converted from one to other. And here another interesting thing is that gamma is a continuous variable, while Poisson is a discrete variable. So we have to be careful when we are computing these probabilities. So let's take a look at this. We have rare events, and this is let t be our gamma variable, where it shows the time to the alpha rare event. In other words, it's a gamma random variable with the parameters alpha and lambda. If the waiting time between every consecutive rare event is an exponential random variable with parameter lambda, and if our variable t is the time to wait until the alphth rare event, then it becomes our gamma variable. Now, let's look at this event, the event that waiting time is greater than t. Okay, now this means that this event means that there are fewer than alpha events that occur in t time. Okay, because if my waiting time is greater than t, it means that I have to observe less than alpha events in this t time. This is the same event. Now, that in this case, when we convert it to number of events in t time, it becomes our Poisson random variable. So now we define a new Poisson random variable with this parameter, lambda t. T is here was the question that we were asked, right? In the problem, for example, we may be asked, what is the probability that it will be greater than 10 minutes? If lambda is given in the unit minutes, for example, if lambda is occurrence of some event in a minute, in a single minute, and if you're asked, what is the probability that I will have to wait more than 10 minutes? I define a new Poisson random variable with 10 minutes as its unit, or so the number of events in 10 minutes, because I will be asking a question about a particular specific minute right here. What's the probability that my random variable t is greater than 10 minutes? Now I have to convert when I'm defining my Poisson random variable, I have to say how many events occur in 10 minutes. What is that Poisson random variable? If lambda was given to you as number of events in a minute, then the number of events that happen in 10 minutes is 10 times lambda. Okay, so if it was given to you, lambda was given to you as number of events that happen in an hour, then you have to again convert it to lambda t by dividing it by if again you're asked something about 10 minutes, and if lambda was originally given to you as in an hour, and then in that case you have to divide lambda by 6 to get the Poisson random variable that shows the number of events in 10 minutes. So in other words, whatever probability we are asked, we convert it to a Poisson random variable in which the number of events is the time in that time interval that we are asked. So the probability that t is going to be, that waiting time is going to be greater than t, this event, is the same as to observe less than alpha events in that time interval, which is this lambda, which is this t, and the number of average events in that time interval t is going to be lambda times t. So here, Poisson is this random variable, and this event is the same thing. It's the number of minutes to wait less than, more than, I mean, the probability to wait more than t is the same as to observe less than alpha events in the same interval. This is a Poisson random variable. If these two events are the same, it means that the probability of these two events are the same. They are the same events, their probabilities are the same. Now, look at this. Probability that t is greater than t can be computed directly. This is the Poisson, it looks like the Poisson CDF, but it's Poisson CDF alpha minus 1, right? I mean, because here, this is less than alpha. Okay, so we have to look at Poisson CDF alpha minus 1 when we are solving this. This is really important. One thing that is here is that probability that t is greater than t or probability that t is greater than or equal to t are the same. So t is a continuous random variable. Whether you have this greater than or equal to doesn't change this. However, on the right-hand side, they are entirely different. Okay, so this is a discrete random variable. Probability that you're going to observe less than alpha events. Here, you're looking at the CDF of alpha minus 1. If this was equality, probability to observe less than or equal to alpha events, that will be the CDF of alpha, which is going to be entirely a different probability. So you cannot put equality on the right-hand side. You have to be very careful. But you can put this continuous random variable. If you're asked the probability that, what is the probability to wait more than or equal, at least t times, including t, for example. If t is included, the probability will still be the same. You will still be able to find it by looking at this equation where there is strictly less than. So if you're interested in the complement of these events, the probability that less than or equal to or less than, it doesn't matter. So the left-hand side, as I said, equality or no equality doesn't matter because t is a continuous random variable. But here, if you take the complement of this, it will mean that you have to observe at least alpha events, including alpha, if you want to wait less than or equal to t minutes. If x is your Poisson random variable, it means that in that time interval, you have observed alpha or more events. So this is that probability. So these two equations that you see here, this one and this one, depending on what is asked of you, is called the Gamma-Poisson formula. And any variable, so you will be given these two things, for example. If you're asked a probability about a time, you're going to multiply these two things, alpha and t, to get your Poisson random variable with that specific lambda for that problem. Okay, so it will be a Poisson random variable with lambda is equal to lambda times t. And you will be looking for your alpha here is going to be the probability that you will be, it no longer is a parameter. So the roles of what are parameters, what we are asked changes. So that may be confusing at first. When we look at an example, it will be clear, but we're out of time. I will take a look at, I will solve that example on Thursday. But in that example, it's going to be clear. So the parameters and the thing that we are asked, what is the probability that we are going to wait more than 10 minutes? That 10 times lambda becomes the parameter of the Poisson, while this alpha, the parameter of the gamma, becomes the thing that we're asking, the probability specific random variable value, specific threshold that we're asking for that random variable. So they change their roles. Therefore, solving these examples at first it may look a little bit complicated, but if you solve a couple of examples, you will get the hang of it. So it's not that difficult, you'll see. And it allows us to solve, refer to the Poisson Poisson table to solve these problems. And you may ask, do we really need this? No, if you can directly solve if you have access to the Gamma PDF, Gamma CDF, you can also ask these questions directly by looking at the Gamma CDF, right? But sometimes it may be more efficient to solve it in the Poisson way, in terms of computing this integral, the gamma function. By the way, also another thing is when alpha is not an integer, we cannot use this Gamma-Poisson formula, right? Because this, when alpha is like 2.5, maybe, yeah, less than 2.0. I mean, we go to discrete space. It will not work. So it has to be an alpha, it has to be an integer in order to use the Gamma-Poisson formula, because our Poisson variable is an integer. All right, so yeah, this is that example, example 4.9 in the book. You may also take a look at that if you wonder about how we solve these problems. But I will, this is where I left today. I will leave today. I will solve this example on Thursday. And yeah, it's like in 2 slides, we are going to finish this. And then we are going to start the normal distribution and talk about and finish normal distributions, and probably talk about the central limit theorem on Thursday. All right. That's it from me today. I will be happy to answer any questions you may have. So I will stop recording now.